Hello, welcome back to my lecture. This is the second chapter's topic, which is MOS inverter configurations. In our previous lecture, we have seen what is a MOS inverter, what is the structure of a MOS inverter, and its transfer characteristics also we have seen. Now, let us jump into the in detail analysis of a MOS inverter by just checking the first step is knowing the different configurations that are possible with the MOS inverter. So the basic inverting component is NMOS transistor, that is fixed. Now that NMOS transistor can work in association with four different kinds of pull-up devices. The NMOS logic is the pull-down logic, and pull-up logics can be altered depending upon the benefits, advantages, and disadvantages. Now the first and foremost thing pull-up device, which is very simple to analyze and understand, is passive resistor. That is R. By connecting a drain resistor in a drain circuit that can act as a pull-up device, it has some advantages and disadvantages that we will see. Now the second possibility is depletion mode NMOS transistor. Why depletion mode NMOS transistor means, while manufacturing itself, we will implant the channel in the transistor. That channel will definitely have some resistance. That resistance will be helpful to develop a correct to develop voltages, which is acting as a pull-up device to pull up the voltages. Enhancement mode transistor, that enhancement NMOS enhancement mode transistor can also be used because once the NMOS enhancement mode is applied, its gate is applied with high voltage like VDD, then it acts as, it will go into saturation and acts as a resistor or a pull-up device. So keeping the NMOS transistor always in saturation region will help you using that device as a pull-up device. The final device is PMOS transistor. That PMOS transistor can also be used as a pull-up device effectively. That we will see in the coming slides. Now, the first one is passive resistor pull-up. This passive resistor pull-up, we can use a resistor as the pull-up device, and this is the pull-down device. If you see the characteristics of the transistor, which already established, we have seen these characteristics. This region is called as active region, and this region is called as saturation region, and this is 0. Now, in this characteristic curve, this is IDS, output current, and this is input VDS. This is output characteristics, VDS. Now, when the input is at 0, output is high. When the input slowly exceeds, output falls to 0. Now what is happening, if you see this curve, you will understand when Vin is less than threshold voltage, NMOS transistor is off. Because NMOS transistor is off, because here NMOS transistor is off, there is no path for this current to travel to the ground terminal. So it has to take this path through resistor. It has to take this path and go to the it has to charge the output load capacitor and make the output high. So when the input is less than VTN, when the input is greater than VTN, then the MOS transistor is on. As the MOS transistor is on, the collector, the VDD, the current from the VDD will find a path through the transistor, through the pull down transistor to the ground. So it will pass through the transistor and goes to ground. As there is a path, discharge path for the load capacitance, now the load capacitance also discharges through the pull down transistor, making the output 0. So when the input is 0, output is VDD. When the input is high, output is 0. Now now the on transistor contributes, the transistor which is in saturation. When the input voltage is above threshold voltage, the transistor will be in saturation. that saturation transistor contribute to a resistance RC. Now this RC, you can see in this diagram, you can see pull up device is RL, and while this transistor is on, this will act as a resistor, small value of resistor, which is RC, channel resistance. So here you can find, you can replace this transistor with a RC. You are taking the output here. Now what will be the output voltage? Output voltage can never reach to 0 because there is a resistor here. This resistor, how much resistance? It is potential divider concept. This potential divider, it is RC divided by RC plus RL into applied voltage VDD. So that is the reason why input cannot reach to 0, output cannot reach to 0, it can reach to VOL. See here, you can see that output capacitance discharges to VOL. VOL is the minimum output that can be obtained. Minimum output. Less than that we cannot have this from this resistor pull-up. To drive the other gates, consider as low level. Therefore, VOL is VDD into RC divided by total resistance RC plus RL, which should be less than VTN. This is the condition. If this resistor pull-up inverter CMOS resistor pull-up CMOS inverter, if you are trying to use this to design your inverters, MOS inverters, it should be capable of driving the following gates. To have that, what we need to do, we need to see that the output or the logic 0 that it produces should be compatible with the preceding circuits, next level circuits. So the condition for that is VOL must be less than VTN, which should be governed by this equation. So what you need to do, you need to choose values of RC and RL such that the total output produced should be less than VTN. That is the condition. So for that condition, to happen, to drive the other gates, consider as low level. Therefore, VOL is equal to this we have seen. The next equation is VOL is equal to VDD into RC by RC plus RL must be less than, because VTN of almost all the circuits is equal to 0.2 of VDD. Now this VDD and VDD gets cancelled. If you simplify this equation, wait, I'll show you. If you simplify this equation, this VDD with this VDD gets cancelled, and RC by RC plus RL is less than equal to 0.2. That means RL must be greater than 4 RC. That on resistance is channel resistance of a NMOS transistor. It should be 4 times of load resistance that is used, must be 4 times of that. Now what is load resistance? A load resistance is a polysilicon material deposition. While manufacturing in the chip, we have to place a particular quantity of polysilicon as a resistance. If the resistance value to be maintained high, what you need to do is you need to place lot of material as resistor. The large quantity of material that will be placed as a resistance will definitely occupy large space. Here you consider you are using some 100 200 inverters or more than that. Practically it will be tough to accommodate so many resistors on a silicon wafer, which becomes expensive or a limitation to the manufacturer or the system. So these are the limitations, broad limitations of using pull-up as a resistor. Symmetrical switching times, because switch 0 to 1 curve will not be same as 1 to 0 curve. There will be a hysteresis because of the resistive material. So that is asymmetrical switching times. RC and RL should be low. The low values of RC and RL will definitely cause a large power dissipation, which should not happen. This RC, to make the RC very small, to make channel resistance very small, what need to do? The basic thing, when you need to have less resistance, you need to make the device larger. Larger devices obviously lowers the component density. When component density is less, there is no meaning of using a VLSI chip. So, and one more limitation is the power dissipation that is incurred by the resistors are always very high. So, the chip area we have discussed. So, those are the limitations of using a resistor. So, the next choice, second choice is using a depletion mode device as a pull-up, because the depletion mode device have a channel already implanted. So this is always on, even though you to make this, to turn off this, what we have to do to turn off this, you have to apply a logic 1. You have to connect this base terminal to the supply, then only it turns off. So the advantage of using a depletion mode device is, because resistor was occupying large space and consuming lot of power, those two problems, all the problems of using resistor, what are the problems that we have faced due to resistor, can be avoided using depletion mode device. In this depletion mode device, pull down device is NMOS enhancement mode transistor, and NMOS depletion mode transistor is used as a pull-up device. If you see this output characteristics of that inverter, what you can see here is, when the input is 0, when the point A, at the point A, input is considered as 0. Now the output is high. When the input slowly increased to point B, when the input slowly increased to point B, output starts decreasing, because one device, because the pull down device have started conducting. So this B point, at the C point, almost both the devices are on. At point C, both the devices are on, because this device is always on. This is also entered into almost entering into the saturation, so the output is falling drastically. At point D, device entered into saturation and it has almost reached to 0. At point E, completely input raised to VDD, output falls to almost 0. In this case also, output is not equal to 0 exactly here, because there is a resistance offered by this pull-up device, which does not allow the output to reach to 0. So mathematically, to prove all this, we need to see these equations. Pull down device is off, and pull up device is in linear region. Pull up device is always in linear region, because it have that implant already made. So pull down, we have to think about pull down device. At point A, the curve of the output voltage Vin is less than Vt, as just now we have seen. Now output voltage is equal to VDD, and that time, because the pull down device is off, current through the device cannot flow, so that is IDS is equal to 0. Now the pull down device, if the pull down device is in saturation and pull up device is in linear region at point B. Now the saturation region transistor IDS is governed by current of pull down device, is governed by kW by L into V in minus Vt pull down, Vt threshold voltage of V in minus Vt whole square. Now that can be rewritten as V in is equal to V, as at the point V in is equal to V out. So you can write V in the place of V in, you can write it as V out. This is that equation. Now when the pull down and pull up device both in saturation, both in saturation when both the devices are in saturation, the equation, because input voltage, this is pull down device. Pull down device is equal to kW by L into V in minus Vt. Pull down device, V in minus Vt pull down, because input is directly connected to this. The other device, input is not connected, input is grounded, so input is not there. Pull up device, input is not there, kW by L into Vt. So pull down device in linear region and pull up device is in saturation. This is the fourth condition. Pull down device is in pull down device is in pull down device is in a linear region and pull up device is in saturation. So pull down device is in linear region. The equation, current equation for the pull down device, which is in linear region, is written like this. Kw by L is can be written as beta into V in minus Vt minus VOL by 2 into VOL. So this is the equation for pull down device. Now now the output voltage VOL, the output voltage when the input is high, when the input turns high, the output almost falls to 0. Now that output falling to 0 is governed by the equation 1 by 2k into V pull up device threshold voltage square by VDD minus V pull down device. So this equation can be in this equation the major thing is K. K is the proportionality constant or the device dimension parameter. The device dimension parameter is beta of pull down by beta of pull up. It is misspelled here. Here it is PU. So W by L of W by L ratio of pull down device to pull up ratio. So the output is not ratioless. There is a static power dissipation because pull up device is always on. Whenever there is a pull down device is also on, both the devices will be in on state. When both the devices either, of course, both the device looks like resistors, acts like resistors, but because both the devices are on, there is a direct path from the supply to the ground continuously, so which is considered as static power dissipation, and it causes lot of damage to your circuit, VLSI circuit, and lot of power being consumed. So the finally it can produce strong high but weak low, because when the output is low it is not equal to 0 but it is equal to VOL. So the next choice is having NMOS enhancement mode transistor as pull up. If the NMOS enhancement mode transistor is used as pull up, NMOS device always turns on for a high input. When the input is when the input is high, then output will become, when the input is high, then the transistor will be on. Then the transistor will be on. So to make this transistor always on, what they did, they have connected this gate permanently to the supply voltage, which keeps this device always on. When the input is at 0, output is NMOS device input is 0, output, this device is off, so the output becomes VDD minus VTN, because this acts as a pass transistor. It needs VGS minus VT to establish the channel. So this output voltage with a difference of Vt appears as the output. This VDD with a difference of loss of Vt appears as the output. So VDD is here and output is here, which is equal to VDD minus Vt. When the input is 1, output is greater than 0 but not equal to 0. Output is again VOL, because both the devices are on during some time. There is a static power dissipation and output cannot reach to 0. Output cannot reach to 0. The limitations of using this enhancement mode transistor is, as we have seen in the last two classes, asymmetry in switching. There is a static power dissipation, just now I have told you, and it produces weak low and weak high outputs. Output is also high output also VDD minus VT, and low output also not equal to 0 but it is VOL. So that is also a long choice. Now coming to the final choice, which is PMOS transistor as pull-up. As PMOS transistor as a pull-up, we can see here PMOS transistor turns on. PMOS transistor turns on when you apply a 0 input. NMOS transistor turns on when you apply high input. But PMOS transistor is reverse. PMOS transistor turns on when you apply low input. So connecting the gate to the ground terminal keeps this device always on. As this device is always on, you just need to think about this device, pull down device. When you turn on this, when you give input 0, output is equal to VDD. And when you slowly raise the input, output turns to 0. And here the problem of weak high has been avoided and problem of weak low is existing. The limitations of this pseudo NMOS, this is also called a pseudo NMOS. The pull-up transistor is always remains on. DC current flows when pull-up device is on. Pull-down device is on. That means whenever pull-down device is on, because always pull-up device is always on, current flows to the ground. That should not happen. To overcome that, you need to have the device parameters changed. The final choice of these are the 4 choices. This topic is another topic which we can discuss later. Thanks for watching. Thank you.